Hey robot makers, hope you're having a good day so far. So do you want to learn how to make your own Pico based plotter? Then this is the show for you. So let's dive straight in. My name is Kevin. Come with me as we build robots, bring them to life with code, and have a whole load of fun along the way. Okay, let me get over to my slides and we can make a bit of a start. Cool. I'm not sure what's going on with that overlay that seemed to have messed up at the very beginning there. So yeah, the inspiration behind this is I love drawing robots. I've always had a bit of an obsession with this. So the BurgerBot robot that I created, version 3 that had a pen that goes right through the middle, and you can actually use that robot to draw things. I did a project way back when using it was a build that somebody else had made. I think they'd used an Arduino, and I kind of converted it to a Pico and to MicroPython, and that was a noughts and crosses playing robot. That was a really cool one, and it had like a little there was like 2 servos that would move the pen around. It was quite clever math to make that work. It also would never lose a game. It would draw a game or lose, never lose, or it would win. We had the Scrolly Wally. I've literally just taken that apart to test out one of the stepper motors for today's show. We'll have a look at that in a second. And the Brachiograph, that was a really cool robot that can draw by doing little sketches. I'll be taking that one along with me to open source, which is only a couple of weeks off now, so I'm very excited about that. And I've always wanted to build my own XY plotter. I've got plenty of plotters already. I've got the professional one, which is the Cricut, that can do plotters with pens and things. I've got the 3D printers. Each one of them can effectively be a plotter. If you just put a pen instead of the filament, you can easily make that into one. But I thought I'd have a go at making one myself, kind of from scratch, without using anybody else's code. So that's kind of the basis of what we're looking at today. So I was looking around and I came across this 3D model. I've linked to this in the description if you wanted to download this one as well. So I've not designed this one. I've kind of just downloaded this one from Thingiverse. So the minimum viable product for this particular project is version 1. I want an XY plotter that can make a pen go up and down, and we can use that to draw pictures on a piece of paper. I want to use a simple 3D printable plotter, so minimum kind of parts for that. Kind of quick time to print as well, little filament. And I want to control it with a Raspberry Pi Pico. I'm a big fan of Raspberry Pi Picos, and I'm also a big fan of MicroPython, so it has to be able to work with both of those. And I also want it to work with G-code and Gerbil, or Gerbil, I think it's correctly pronounced. I was looking to see that the person that created this, and I think they pronounce it Gerbil, with the emphasis on the Ger, apparently. So yes, if we can make this plotter run on Gerbil code, then we can do all kinds of clever stuff with it with other software as well. And for bonus points, if I can squeeze this into this project, I want to use end stop. So I bought a whole bunch of these little micro switches so we can put them onto the plotter. This 3D model doesn't have these, so this will enable the plotter to move along the carriage and effectively home where you'll find that the home position for each of the X and the Y positions. Using an SD card would be quite cool as well. We could potentially download files to that, and then with version 4 we could potentially download files via a web interface, so we could jog the controls, we can make it move up and down, left and right. I've made a bit of a start on that, but that's not something I can show today. It's not there yet. So they're all the things I want to be able to do with my Raspberry Pi Pico and a 3D printable plotter. So what is G-code? I talked about that just a second ago, about we want to be able to use G-code. So G-code is a kind of standard language used in all kinds of CNC machines, 3D printers, laser cutters, similar kind of devices. And it stands for geometric code, and it consists of a bunch of commands that tell the machine how to move. And it's human readable as well, so we can type these commands out and kind of understand what's happening, and we can get software that will generate all kinds of G-codes to plot out a picture, or it can laser cut some model that you want to print out or whatever. So the commands usually start with a letter like G, which is like move. We have M, X, Y, Z, F, S, etc. And they're usually followed by a number as well. So G-code defines the movement type. So is it rapid movement? Is it linear movement? The coordinates, the X, Y, potentially Z if it's a 3D printer. And the feed rate, or the spindle speed, is usually provided as well. So how fast do you want this thing to actually cut or move? We don't need a feed rate in our case because we're not feeding filament through. We're not got a spindle that's cutting stuff away. We've simply got a pen that we want to move up and down. We're going to do that using one of the stepper motors. And it's typically this software, the G-code is usually generated by CAM software, computer-aided manufacture software for 2D and 3D models. So it would be really cool if we can create the kind of shell in our MicroPython code and have that connect by a serial cable, by UART, to other software that can then feed it to the G-code, so we can kind of separate out those concerns. And G-code, like I said, is human readable and editable, sort of that manual fine control. So we need to learn a bit about what G-code is. So Gerbil is a lightweight open source motion control software for CNC machines. Runs on microcontrollers like the Arduino Uno. I've got a little Arduino Uno clone here. That was originally what this was written for. But it's also been ported across to chips like the RP2040. Now that is C code, not MicroPython code. So we can't just take that library and immediately use it. We have to essentially start from scratch, and for each G code we have to make an equivalent one in MicroPython. I've not found anybody else that's done that so far, so I've had a good stab at that for this particular project. We'll see how far that gets us in a second. So Gerbil interprets the G-code and translates into steps and direction signals for stepper motors, and it supports 3-axis motion, X, Y, Z, and it has features like homing, soft limits, which is how far do you want the carriage to move, X and Y and Z, before it actually stops, and you can define those in software, so that's a soft limit. We can have status reporting, so is there an alert, have you told the carriage to move further than it physically can? And you can also have things like jogging, where you can move just using some arrow keys the head around, the end effector around wherever you want that to be. And typically with jogging, when you move that around, it doesn't change the state that's recorded where the thing is, and this is so you can define control where you want the head to be, and then you can effectively zero that to be the origin point. It will also communicate with the host, so we have things like the Universal G-code Sender, UGS. There's a BCNC, CNCJS, which I've downloaded UGS and CNCJS. We'll have a look at those in the demo as well, just to see how they work over serial. And designed to be simple, deterministic, real-time safe for small embedded systems. It's widely used on DIY, CNC laser engravers, and for educational machines. So I want to kind of emulate what this Gerbil does in our own software, our own firmware that we're going to create. So I found this really cool design by, how do you pronounce that, ICOM, is that? Put a link to the description if you want to download the same model yourself. It's quite quick to print, the pieces are quite non-complex, they don't need too much support, and they only took a couple of hours to print all the parts. And it is just a couple of parts. You just need a bunch of M3 screws, I think it was, and I think some kind of wood screws, the screws that you can screw into plastic 1 or 2 times quite firmly. If you do it more than twice, they become quite loose after a while. I prefer nuts and bolts myself, because you can tighten them and untighten them as many times as you like. So it's easy to recreate this kind of model in Fusion 360. That's what I'll be doing to modify these parts, because they come in as STL files and we can't really edit them not too easily in Fusion 360. So it's easy just to get the old calipers out, wherever I put those, and just measure each of the parts individually. I can't remember where I put my calipers. I usually have them just to hand over there. Anyway, so I would measure out these parts once I printed them out, and then reconstruct them in Fusion 360. And that means we can add our own things, like we can have these little end stops somewhere on the model that makes sense, and we can also add some other features as well if we like somewhere to actually hold the Pico and all the other control boards that we have as well. So it uses 3 of these. I'm just going to grab this one off the desk here and pull all the cables out to show you this. This is a 28 BYJ stepper motor. I'm not sure what the extra B is on there. So these are quite common. This one's currently got a little, if you can see that, that's not normally on there. That's just for the project that I had before, which is the Scrawly Wally, so it had one of those timer belt things on it. But I've put a little sticker on, so when we actually move this, you can see it moving around, because it's quite hard to see the tiny little spindle moving around. So these typically come with a driver board, so that's the driver board. We'll have a look at that in a bit more detail in a second, and it's got some LEDs on there. And like I said, we'll plug this into a Pico and actually start programming that in a second, just to show you how all that works. It's got 3 of those, one for the X, one for the Y, and also one to make the pen move up and down. The pen kind of goes through a little hole, and we simply just tilt the pen on an axis to make it sort of make contact with the paper or not. So not sure why that they've chosen that particular route. Most other plotters have some kind of regular hobby servo, and the pen will go up and down quite vertically. It's just a different approach they've used in here. So these are the kind of electronics I've got for this project. We have this little servo helper board. These are available from the kevsrobot.com website. I think they're quite cheap as well, actually. So this simply allows you to connect, up a bunch of like hobby servos or whatever you wish, really, and you can have access to that, to the signal pins at the top there. You can kind of break them out, and on the side there we've got a common voltage and ground as well that's shared amongst all of the different things. Now, although this was designed for servos, we can actually use this for any kind of project that requires a common voltage that's kind of an external power supply, and these motors need a good 5 volts, and we might not be able to draw enough 5 volts through the Pico. That's not really what you want to be doing if you can help it, but we'll have a look at, as one of the questions we will ask, can we drive all this project from the Pico, or do we need to have an external power supply for this? So the servo helper can help us just wire all that together. We've got the servos themselves, the 28BYJ. I'm not sure, I don't think the B is actually required on that. I've seen that twice now. I'm not sure that's a typo or whether that's actually a thing. And we've got a bunch of DuPont cables as well. I bought some of these just for this particular project. So these come in a bunch of varieties. Let's open them out and show you what I mean. There's essentially like 3 different types in these packs. So come in all kinds of colours, and you can kind of just like peel these off to make little bunches of yourself. So the first type is this one, where it has the female ends on both ends. Then there's another one which has a male on one end and a female on the other end, and then the other one is both male on each end. So you get a pack typically of each type in there. So does it say how many you get? But yeah, these ones are LED, and they're not too expensive, so it just means we can wire things up kind of semi-permanently, but we can take them apart at the end, or we can just move things around if we need to and put it onto a different project. And of course I've got a Pico as well. So on this particular project, I will be using a Pico 2W eventually, but to begin with we just need a Pico, just a regular, doesn't need Wi-Fi, doesn't need to be a Pico 2. We're just going to go with a very basic one for now. We don't really need the extra power of the Pico 2. So this is a bit of a close-up of that servo helper, just to understand what we'll be using this for. So the top row there, we will connect those things to the GPIO pins on our Pico. Then the bottom pairs of kind of triplets of cables that we have there, the connectors. The very bottom row is the ground pin. The middle row is the 5-volt rail. And this is quite clever when they designed the servo connectors. The 5-volt being in the middle means that you can never wire it the wrong way round. You can never, like, you know, if the 5 volts was on the top and you put the cable in back to front, it would essentially be reversing the polarity and damaging your microcontroller. Having it in the middle one means that whichever way you put it, it's the 5 volts is always going to be in the middle, and all you'll be mixing up is your signal pin and your ground pin, which typically is okay to do. But, you know, really the right way round. So we're not going to be using hobby servos, we're going to be using stepper motors. And stepper motors require 4 cables per stepper motor. So we've got a bunch of cables coming off here, and we need to have 4 control cables per servo, and also a voltage, so a ground and 5 volts per servo. So what we can do with this servo helper is we can actually use columns 1, 2, 3, 4 for the first servo, for the first stepper motor, 5, 6, 7, 8 for the second stepper motor, 9, 10, 11, 12 for the third stepper motor. They only need to have one set of 4 pins, if you like, connected to the 5 volts and the ground as well. So we only need to use a couple of those. But we can then use either the Pico or a bench power supply for the voltage in. We just need to make sure the ground is connected to the Pico, and if we're using a bench power supply, connected to that as well, just so we don't get any funky things happening. So Hope that makes sense. It's very, very simple to use these servo helpers, and it's just an extra step in wiring this thing up. You don't actually have to have these. You could just wire everything directly to your Pico, but I just wanted to make this interchangeable. So how do these stepper motors actually work then? They're quite cool how they actually work inside. So they've got a number of different magnets that are arranged internally into the to the main body of the stepper motor, and they can be turned very accurately, one step at a time. So the motor will start at the very first position, and the very first magnet will be energized, and therefore will be at the sort of top position. We then want to move the stepper motor to the next magnet, so we will switch the next magnet on, turn off the first magnet, and that will make it sort of turn around a little bit, and we'll keep doing that until we get to the very final position. And because these have been done very, very small increments at a time, we can very finely control the stepper motor itself. They typically have like a gear on there as well. So the magnets, there's 4 phases of the magnets sequence, and you can see in that little table that we have there, we've got 4 A, B, C and D. So the first position, we've got A magnetized, energized, everything else is not, and that means that we're in the first position. Then we'll energize B and A, leave the other ones off, then we'll just leave B on, and we work our way through that particular sequence there, and that will actually have the motor turn round kind of one cycle of the steps. And that's considered to be one step, the whole sequence. So they actually have an LED for each of these magnets, so you can actually see the thing running, which is quite cool. And when we do a demo in a second, I'll actually show you that. It's quite cool to actually see this kind of working. And it does feel very, very manual that we have to switch on with a GPIO pin each individual magnet to step through the sequence. And we've got there 4 IN1, IN2, IN3, IN4, and they correspond to magnets A, B, C and D. And we need 5 volts in as well to power the stepper motor. It uses quite a bit of current. So how is our software going to work? So the software stack for our little plotter, we're going to have MicroPython kind of at the bottom of the stack. We're going to have a driver that we're going to write that's called stepper.py. We're going to have a G-code interpreter that can receive G-code and then turn that into movements. And then on the top of that, we're going to have our main.py, which is the kind of main wrapper program that will accept G-code commands and then kind of pass them to the stepper motor. Now, the other thing we want to have external to this is something that can convert like an SGV file, which is like a standard vector graphics file, into G-code. So there are bits of software that are free out there on the internet. We can do that. Once we've got all that G-code, we then want to stream that G-code to our plotter. So we want some software such as that CNC.js or the UGS, Universal G-code Sender, to do that as well. Both of them are free, and they both run on all platforms. We'll have a look at those as well in a second. So let's make a note to look at that, UGS and CNC.js. And then if we run through all those, we should get our plotter to draw the picture that we're after. So if you like these kind of videos and you want me to make more of these, please drop a like on this video. Let me know in the comments if this is something you're interested in, if this is something that you'll be wanting to build. This is probably going to be part 1 of at least part 2 videos, because the project isn't finished yet, and I'll talk to you exactly about where we're up to in that in another slide or 2. And if you've not subscribed already, please subscribe. It means so much to me when people subscribe to the channel. I can't tell you how much joy I get from every single subscription. And I do go live every single Sunday, come what may. So 7 o'clock British summer time currently. And we just had midsummer yesterday. Yes, it was yesterday, wasn't it? So yes, we're now on the long summer days ahead. So fail more. That seems a really odd thing to say, but let me talk to you about failure. So typically when you're working on a project, you go through a bit of a roller coaster. You'll start out with an idea. So this one, I want to make a 3D printable plotter using MicroPython and a Raspberry Pi Pico. The dive is where you jump in, you start exploring all the software, all the tools, ordering the parts, getting everything together. Then we get to the tangle. This is where things start to kind of fall apart and not necessarily work the way you want them to. And this seems to happen quite often in projects. Rarely do we have one where it just works. I think the only project I've had recently where things just worked first time was the Thinkman, which was like that AI Walkman that I built. Everything on that one just seemed to work fine right off the bat. Whereas this particular project, yeah, things have kind of gone a little bit awry. This is where we have to pivot. We have to adjust course based on what's working and what's not working. So I burnt through an entire day on Friday trying to connect my software to this universal G-code sender so I could send the plotter some commands, and I just couldn't get that to work, and I tried everything to do that. So at that point I had to change track. So instead of using UGS, I then use this CNCJS. We'll have a look at exactly what that is in a second, so that makes sense. But that bit is hard because if you're not getting results and you keep trying different things, how much tenacity do you need? So burning through an entire day to try and get something to work, that, you know, for my time budget, that's quite a lot of time to put into it. And then a breakthrough, at some point you'll reach a point where things do start working again and you've got that kind of relief and you can move forward in your project. I typically try and polish my projects, so I will write them up, I will put a bill of materials together, a tutorial, I'll publish all the STL files or the G-code files or MicroPython code, whatever it is, to GitHub, and also write a blog entry about that, and possibly even create a little mini course for people to be able to do the same thing. And then after I've done that, I'll reflect on it, look back what worked, what didn't work, and what's next, what's the next steps. I do like to put on each of the projects, if I was to come back to this, what would I do next? And that means if I return to that project, I've got a ready list of things to look at. So that's just kind of how I look at projects. And the messy middle is the bit that's really, really hard to get through. A lot of people can give up on that bit. You just got to stick with it. So John Maxwell famously said, the more that you do, the more you'll fail. And the more that you fail, the more you'll learn. And the more you learn, the better you get. So I like that. That's why you need to fail more, because that's where the learning happens. If everything went right the first time, you wouldn't really learn anything, and you probably wouldn't feel that you've actually stretched or developed in any way. So, but it can be frustrating at the time when you're trying to get something to work and it simply doesn't. So what you need to do is run some tiny experiments. So when we're looking at this, building this plotter, how do we make stepper motors work? So we've done some research, we've found out that we need to control it using 4 pins, and we need to have a sequence of those 4 pins to make them actually move. But how many steps does it take to do 1 millimeter of travel? We can figure that out today. Let's do an experiment on that in a second. How fast can we move them? We can also try that out as well. So is there a speed that this stepper motor will work at? Will it zip across like some of these 3D printers you see, or is it going to move really, really slowly? Do we need to have an external power supply, or is the 5-volt pin on the Pico enough for these to work? We can find out, we can give that a go. I don't mind burning through a Pico to show you if that works or not. And then the G-code interpreter, what's the minimum codes we need to move the pen around? So we know we need to be able to move X and Y and pen up and down, but is there anything else that is like mandatory that we need to have? How do we connect it to this Gerbil streamer, or this G-code streamer? Can we write all this in MicroPython? Is MicroPython fast enough to be able to interpret these commands from the streamer? Is there any safety features that we need to include? So, you know, if we tell the stepper motor to keep going left, is it going to go left forever? So some 3D printing software, for example, will have things like thermal runaway protection. So it'll stop the head end from heating up infinitely, because that will just cause a fire. So typically they will have something where if it's not detecting a change, but it's telling the head end to get hotter and hotter and hotter and hotter and hotter, if that temperature isn't changing, it'll just say stop and the whole thing will shut down. So do we need any kind of safety features, and what will they look like? That's something that we need to think about, a little experiment to do. And then what else? So the 3D printed model, does that work as advertised? Is that a good model? Is there anything that we need to improve upon it? So I've already talked about putting some end stops on there. That doesn't have that currently. How can we make it better? End stops is going to be one of the things I do. Will it fit a Sharpie? So I typically like to use Sharpie pens on my projects, and the hole where you sort of put the pen through doesn't actually work with Sharpies. So What do we need to do? How can we measure? How can we improve that? How do we organize all the electronics? So each of these little control boards, there's going to be 3 of these. There's going to be a Raspberry Pi Pico and potentially like a power supply, depends on how far we go with this project. How do we organize all them? Are we just going to have them loose on the desk? Are we going to hot glue them to like a wooden backing or something like that? What's that going to look like? And then this Gerbil stream, this G-code streamer, what's the best one that's on the market? Are they paid? Are they free? Can I convert an image from SVG to G-code? How much G-code do we need to learn before we can actually draw images? So lots of little experiments that we can think about. And if we write our code to answer each one of these questions, then it means that it's a much more bite-sized approach, and we're only looking at one thing at a time, and collectively they will help us build a better project. So they're the tiny experiments that we're going to be doing. So let me show you some of the progress I've made so far in this project. It's not finished just yet. So I've got a stepper motor class that we can use. So I think I created this one for the Scrawly Wally project that I did a while back. We'll have a look at this code in a bit more detail, larger, clearer in Thonny in a second, but just you can see there it's got 4 functions. There's an initialization function, there's a set step, and that activates the motor calls depending on which step pattern we've got. You can see we've got that step sequence there as well included. We can move, we can say rotate the motor by a given number of steps in the specified direction, so plus or minus 1 to set the direction, and then we've even got a stop function as well, so that deactivates all the motor calls and stops the motor to reduce current draw. So we should probably do that stop command at the very end of any of our drawing commands. Then we've got the G-code interpreter. I've made a really simple G-code interpreter. So on there, again, there's an initializer that will initialize the stepper motors for the different positions. So we've got an X, Y, and Z. The Z is the pen one. And then we've got a position for each of those that we can record. We can parse a line of G-code, so we get a G0, G1. We can then move the motors accordingly and update the track position. We can set the position, so we can set an internal position tracker for the X, Y, Z. That simulates that G92 command. And we've got a jog, which moves the motors relative distances for each axis without updating the internal position. And that mimics the kind of Gerbil jog behavior as well. So we've got functions for each of them. You can see there's not a lot of code there to do that, so these can be quite straightforward. So for part 2 of this project, I'll be fixing the issues. I think I've got a short circuit on the wiring loom that I've created there. We'll have a look at how I know that and what we can potentially do about it. It's not bad enough that it stops the thing working. We can actually show a demo of this today, but I am detecting a short circuit on my bench power supply because it tells me if you're short 2 of the pins together. I'll update the, I've not showed you any slides on the actual wiring of this yet, so I'll create some wiring and electronics slides on that. The 3D printable parts, I'll be updating those so that they have these end stops as well. And yeah, an end-to-end drawing workflow will have a system that works, so we can put in an image, drop it in there, and we can have the plotter draw it. I'm not sure for part 2 whether I will have the web interface working, but that is also something I want to be working on. I've got some code already for that, particularly for the jog. There were the buttons I wanted to have there. And I also wanted to have like a terminal of what commands are we receiving from the streaming software. So let's have a look at some tiny experiments, shall we? So let's get my demo notes up here, and let's get over to Thonny. So I'm just going to load up Thonny, and I'm also going to show you what we have on the desk. So the first thing we'll do is we'll just wire up a stepper motor and control it with some of our code. So the first thing I will do, I'll just jump over here. So I've got a Raspberry Pi Pico here. This one is I think Pico WH. It's got the header pins on it, and I've got some of these DuPont cables already wired up here. So the red and the brown, I'm going to connect these to the Pico directly, so I know that that pin there, pin 40, is 5 volts coming from the USB, and pin 38 is a ground. So that's what that looks like to get some power into our little control board. And then what I'm going to do next is, I can see there I've got the iron 1, iron 2, iron 3, iron 4. So that's yellow, orange, blue and green. So what I'm going to do is just simply connect these up. So yellow is going to go to GPIO 0, orange is going to go to GP1, Then we have the ground pin, so we just have to miss that one out. Then we have the next two, so IN3, IN4, and they're also mirroring IN1, 2, 3, 4 there as well. So that's all we need to do to wire up one stepper motor. I'm going to plug in my cable there as well. Okay, so if I just leave that there, I'll put this little piece of post-it note on there just so you can see when we actually do the code, you can actually see that moving around. Right, so what I'm going to do, I'm going to write some code. So let's go to our stepper motor code first of all. Let's just go full screen on this. So this is that code that I showed you on that slide earlier. I just wanted to go through in a bit more detail what's actually going on here. So I created a class that is called stepper motor. I'm importing pin because we need to be able to connect to GPIO pins, and I'm also importing the sleep US, which is like the microseconds, I think it is. So the first thing, this is the step sequence. This is essentially a list of values. So we've got 1000, that's the first step, then 1100. So each of these columns is like the magnets, the four magnets that we want to switch on and off. And this sequence is the sequence. If we run this, it will continually rotate the end of the stepper motor. So that's simply called step sequence. So in our initialization, we're going to take in 4 GPIO pin numbers. So that's IN1, 2, 3, and 4. And potentially, if somebody wants to provide a delay, we've got a variable there called delay US. And we're going to default to 1500. So that's something like 0.0015 steps per second. And then the coils, we're going to have those as 4 pins. So pin IN1 is going to be pin out, so it's an output pin because we're going to be controlling the stepper motor with each of those. And then the self delay, this is going to be whatever that delay is that's passed in, so 1500 is the default there. So set step is going to say for each step that we've connected in there, so for IN coil, so it's going to go for each of the different pins there, and it's going to enumerate self coils and then pass in the step value that we've passed in there. So that's going to help us step through the sequence. We'll have a look at that in a second. Moving is how we want to essentially move our stepper motor. So how many steps do we want it to move by, what direction, backwards or forwards. So by default direction is going to be 1. So that's like a positive direction, clockwise I think that should be. And then the sequence will be the step sequence that we defined above. And if the direction is greater than 0, so if it's 1, otherwise we reverse the step sequence. Colon -1 means just take that sequence that we've got here, but start from the bottom and then count upwards. So that's what that colon -1 means. It kind of reverses the sequence for us. And then for each step in that sequence, we're going to step round in that sequence. We're going to set the step to that particular position, and it will basically set the GPIO pins to whatever on and off values they need to be from that step sequence. So that's what that code there does. And then stop will simply just say step all the steps to be 0, and that switches the motor off in effect. So that's all we need to have for our stepper motor. Nice and simple. And if we look at this code here, we only need to have one of these for now. So let's just change that there. So we've simply just got this X motor. We've just got 1 to begin with, and these are the GPIO pins 0, 1, 2, and 3, and they correspond to IN1, IN2, IN3, and IN4 on our stepper motor. So we're going to import stepper motor from our stepper class. So if I just click on the stop button there, that should connect to our Pico that we've got attached. So the first thing we need to do is upload that class to our Pico. It's already on there, so that's fine. I've also uploaded that G-code interpreter. We'll have a look at that in a second as well. So if we want to run our code, I'm just going to switch over to this view here so we can see the code at the same time. And what I'm going to try and do, if I can do this, is show you the code and the console at the same time. Right, and then let's just get our stepper motor into view there. So let's now run our code and see what happens. There we go. Now all the lights appear to be lit up continuously there, and we can see our stepper motors spinning around reasonably fast in a clockwise direction. So and it's going to go for 1,000 steps because that's what we've said in our for step in the range 0 to 1,000. So it's going to do 1,000 steps and then it's going to stop. So that's in the one direction. If we do -1 and then run our code again, it's now going to go anti-clockwise for 1,000 steps. As you can see there. And the thing is, it's very, very quiet. If I move my microphone over to it, let's see if you can hear it. It's barely audible at all. Very, very quiet indeed. So this is one of the nice things about this. This is going to be a very quiet plotter. So that's how we can change the direction. Now let's play around with the speed. So once we've set up our motor, we can say xmotor dot delay us equals. So let's try 2,000 to begin with and see if that works. So that's moving. Let's try 3,000. That's going slower, so let's try faster then. Let's try, instead of it being 1,500, let's try 1,000. So that's pretty fast. Can we go faster than that again? Let's try 500. Yep, so we can go 500. That's quite impressive. Can we go 250? Nope. Doesn't seem to like that. That's too fast. There's too many operations being sent and the magnets can't energize. So we can probably find the sweet spot. So can we do like 300? Nope. Can we do 450? I can hear it trying and it's missing a few steps there. So 500. 500 looks like the absolute top speed that we can do there, just for reference. So that's one of the experiments we wanted to know, was how fast can we turn these stepper motors. But I think the default at 1,500, although that looks quite slow, it's probably a reliable speed. We're not going to miss any steps and it's going to work just right. So we can certainly put on our code there. Is the fastest speed. Like so. So that's just one. So what I've got over here is I've wired up, just move the power for a second. I wired up a Pico with 3 stepper motors, and I've also wired this into a little wiring loom, which is the servo helper, and it just means I can put either an external power supply or a regular power supply. So we can either let's try it with from the Pico itself. So if I just wire these up and connect that up, so the ground is going to go to pin 38 and the power is going to go to pin 40. And let's disconnect this one and then wire up. Just doing this slightly off camera here, the Pico. Okay, so I'll probably just need to reset that on the console, and let's just try this now. We're going to edit uncomment out the Y and the pen as well. We don't need to have that speed thing. The default is 1,500. We've seen that that works fine. Okay, so what I'm going to do, I'm going to run this code and we should see this stepper motor move this sort of toothed thing across. I don't know if it's going to go plus or minus. We'll have a look at that. We'll see if the pen moves around. I can bring this, if I can zoom that in or out. No, that's about as far out as we can go. And also we can see that this one should bring it in the sort of y-axis. So let's give this a go. So we can see that's moving positively. So I'm going to stop that and make that one positive, and we also need to uncomment out these other 2 as well. So let's try that now. Okay, so you can see that the plotter is moving quite slowly. You can see the pen was rotating, but now let's just stop that. So the issue we got there is it's a failure because the pen was trying to push against the paper, like the pen was trying to push that way onto the paper, and we didn't want it to do that. We want it to only move maybe 90 degrees. So we need to think about that for our future code. But if I just take that off there, we can see that that's now rotating round, and we can see that this is getting very, very close here to the end. We can also see this is getting pretty close to our controls as well. So let's just stop that. And let's just make these all now negative and see if we can get them all to turn in the other direction. So there we go. Yes, that seems to be working okay now. Now, interestingly, I've noticed this pen one doesn't work reliably, and I don't know whether the stepper motor itself is not happy, whether the wiring is incorrect, or something else. Now, looking at my my bench power supply, I've not got that connected up to this at the moment. This is all being drawn from the Pico through that 5-volt rail. So the way that this works, as I understand it, is the 5 volts that's coming from the USB cable from my laptop. The first 5 volts of that is being sort of pulled out and connected to pin 40. It doesn't really run through the rest of the Pico. It's just being redirected there. So we can take that feed and we can draw other things from that. But these stepper motors can get quite warm. They can draw quite a bit of current themselves. Does it say on the actual thing? It doesn't say what the actual current draw is, but I know it can be quite a bit. So how much power can my laptop provide to these? And really, should we be doing that through USB? Should we be probably powering it through a separate power supply? So I have got a bench power supply. I've got that wired up, so we can actually connect this up to the pin on the servo helper, and we can provide an extra 5 volts into there. So if I do that, I can immediately see that my power supply is saying that there's a short. It's got the CC short circuit light is activated. So if I just run the stepper code again, it still works fine. Let's just change the direction of those again so that they don't go past the endpoints. So it's still running, but I can see that that pen one isn't running. So it's not that there isn't enough power being provided, because I was wondering if it was just there was so much power being drawn by all three of them that one of them was just not getting enough power to energize properly. That doesn't seem to be the case. I'm just going to take that away now, and the lights seem to be appearing to be full brightness again. If I just show you that on here, you can see the lights are full brightness. If I connect up the power pin from the bench power supply, they drop. And if I run that again, let's just stop that and then start that again. Yeah, they still seem the same brightness, and the pen's rotating this time, but I'm still getting that short circuit. So I'm not so keen. That's one of the other things on this method of raising and lowering the pen, because one of the issues with this 3D printed model is the pen holder. I'm not sure if I've got one of the. I printed out a couple of these different sizes, and essentially the round part of the thing scratches against that kind of X piece, and that friction causes the motor to detect that there's some issue. And I don't know if there's some circuitry in these or not, but it seems to stop when it has too much resistance. I don't know if that's just the motor can't provide enough power and it stops, but it seems to back off and go in the opposite direction. It could also be a faulty stepper motor. It might be that I burnt that one out previously, so I can swap it out with a different one. These aren't too expensive, so I can just buy another set just in case that's one of the issues there. So that is the testing of the stepper motors. We've tested the speed, we've tested the direction, we've tested one and then multiple. Multiple seems to work fine, and the speed is probably quick enough. It's not going to be the fastest stepper motor in the world. Now, one of the other things that we can do is we can get this to draw. If I push this pen, it's just in the perfect position actually for drawing. So if I just push this here, put a little bit of blue tack through on this one, just to give it a bit of extra friction. Just trying to get it so it touches and makes contact with the paper. Okay, and what I want to understand as an experiment is how many steps do we need to turn to make something one centimetre. So let's think about how we would do this in our code. I'm going to take this stepper and I'm going to create a new file. Let's just move this down a little bit here. So we don't need the pen, we can get rid of that. Let's get rid of the pen. On this one we're going to just use the y-axis, so we don't need the x, so let's get rid of that. What we want to know is, so let's start out with 100 steps and let's see how far 100 steps is. So what I'm going to do, I'm going to get another coloured pen. I'm going to make a mark on where we're starting from, and I'm going to measure how far it draws with 100 steps. So hopefully it'll go in the right direction. Let's see what's going there. So that didn't move very far at all. And it's not particularly making a lot of contact with the paper either at the moment, so we can't actually see a nice line that is drawn, which is quite frustrating. What we could also do is we could get it to draw 1,000 steps. But given the position that we're in, we're right up against here, let's do that in the opposite direction. Let's do minus. So we're starting from the bottom mark, and I'm gonna hold down the pen a little bit to see if we can get that to actually make contact with the paper. Right, let's run this. Let's see if we can get this to draw. Of course the paper moved a tiny bit then. And then we're going to get to 1,000 steps. Okay. So we've now got enough that we can actually measure that. We can see how far does that translate from steps to millimeters. So if I go from the very top down to the very bottom is 9 centimeters. So 1,000 steps is 9 centimeters. We can make a note of that, and that's a combination of the size of the little gear that's spinning round. I did have some other ones printed out of that, but I can't seem to see where they are now. Anyways, so we can just make a note of that in our code. So 1,000 steps equals roughly 9 centimeters. We could obviously do a lot more accurate for this. So let's do steps. Let's call this one test steps 2 centimeters dot pi. So I hope you understand. This is kind of how we go about figuring stuff out. We can use little experiments to see, how far, get the answers to various different questions. How far do these things turn, and so on. See if there's anything else we wanted to look at. So I've got some notes here on the wrong screen there. So how do we make the stepping motors move? How many steps for 1 millimeter of travel? Well, we know 1,000 is 900, so we can work that out. How fast can we move it? We've seen that we can move it 500 steps, 500 milliseconds per step. That seems to be microseconds, even 500 microseconds per step. Do we need an external power supply or not? We don't actually need it, but we probably should use it for our projects because we don't really want to have all that current running through our Pico. These things can get quite warm when they're kind of, even when they're idle. Just if there's any energy going through them, we can see they've got they're currently magnetized. We've not told it to stop, so maybe we should just do that at the very end. So we could just have a Y motor dot stop. So if we just comment out this code, I'm typing code here and you can't see what I'm doing. I'm just going to comment out that and basically just going to get it to stop. So Y motor isn't defined. Let's just make sure that's defined there. So you can see now that very first column there's no lights. Let's just do the same for the rest of them. So if we have the X motor equals a stepper motor, I think we had it 0, 1, 2, 3, and we can have X motor.stop. Let's run our code again. You can see those lights have gone off. They're now no longer going to be drawing current, and we can do the same with the pen one as well. So the pen motor equals a stepper motor. That was 8, 9, 10 and 11. We can just add that to the list of our commands there. So do you understand why that is necessary? Let's run that code. And again, the lights have gone off now on that very end column there as well. So by having no lights lit up, that means there's no magnets energized, and therefore there's no draw currently on the stepper motor, and therefore they'll not be getting hot trying to maintain that position, because that's what that energized position actually means. It also means that we can rotate the stepper motors. If we wanted to sort of manually move things around, we need to make sure the motors are stopped and they're not, the magnets are not drawing any current to be able to move these things around. Cool. So that was the questions that we had for the plotter. G-code. So what's the minimum G-code we need to move the pen around? Let's have a look at some G-code, shall we? So I've created a G-code interpreter. So the first thing it's going to do is just create a bunch of motors, and this is going to convert any G-code that we send in. It's physically going to move the plotter around. So we're going to start our position off as being 0, 0, 0. Now, the issue with this is when we turn on our plotter, without using some kind of end stop device, we will have to manually move the X and the Y and the pen to what is the home position, and then tell our code that it's now homed. We would have to jog that manually each time. Most 3D printers, laser cutters and so on, they use these end stops, these little micro switches, and it's simply an on-off switch, but they've got a nice spring to them, and they have these nice long arms to them, so that you can physically have this connected to one of the X or Y things, and then when it gets to a position where it stops, it can detect that that's the end position, and it can then mark that as being 0. So we can add to our plotter an X and Y end stop, and it only takes 2 extra pins on our Pico. We've got plenty of pins on there, so that's not going to be an issue. So we need to have that in our code somewhere. Otherwise, without that, it's going to be a manual setup each time we switch on, or each time we run our code. Parsing a line. So we need to receive a line of G code. I'll open up a file and I'll show you what some G code actually looks like. So let me just find. I think in my downloads folder, I have. Here we go. Some G code. So let's open up this ABC. Let's open it up with text edit, which is the default. There we go. So this is some G code. This has been generated by Inkscape with this G code tools plugin. So M3, that's the header end. G21, all units are going to be set to millimeters. Start the cutting. So these brackets are just comments. So anything that's in the comments is got brackets. And then G00, so this is moves the Z to 5, so it's going to move it up, I guess. So it's hovering above the surface. Then we're going to say move the X and the Y to 25 by 9. Look at all these decimal points. How accurate is that going to be? So if these are millimeters, 25 millimeters, do we really need 6 decimal points of millimeters? Our 3D printed thing isn't going to be that accurate, so you could probably knock off most of those decimal points, I guess. Then we're going to have G001. That's going to move the Z. In this case, it's going to penetrate. It's going to cut through. It's got a feed rate there as well. So this is probably for like a laser cutter or something that's going to mill away material. So anyway, we've got the F, which is the feed rate. That's to do with that. So you can see that each one of these is going to move the head around in an XY. So we just need to be able to do these G1, 2 and 3 positions for each of them. And they got end cutting ID, and then it's going to do another one as well. So it's kind of broken down into different sections. So let's go back. I'm going to open up some software, which is CNCJS. Let me just open up this. This one seems to work okay for me. And then we'll have a look and see how we can connect to that. I'm just waiting for that to show on the screen. With it being like JavaScript, it does take a couple of seconds for that to sort of load up. It's like Python, it's interpreted. Okay, it's going to wait for that to load up. Okay, so if I now go to, so we can't do that, we need to connect to, I'm going to start and stop that. So when I disconnect and connect up my my MicroPython Pico, it runs main.py, and main.py is currently my G-code interpreter. So if I now find that on one of these ports, why is it not let me do that? There we go. If I connect to there and open it, it's going to make a connection. I'm going to talk you through how this actually works in a second. But I can now upload some G-code. So I'm going to go back to that one that we just looked at a second ago, which was that ABC thing. So I'm in my downloads. And where is it? The CNC plotter one, files, and then ABC hatched. So the code that we just read, that's what it actually produces. And what I want to be able to do is press play and have my my plotter actually interpret that. And we can see that the lights are flashing on and off. We're getting different positions on. If I move this up here, you can see it's going through each of the lines. But our actual plotter isn't doing anything right now. That's probably because we haven't got the commands being interpreted properly. So we need to work on our G-code interpreter. But this is the kind of flow that I want my plotter to do. So how did I get that to, when I plugged it in, detect that it's a G-code device, a gerbil compatible device. So let's go back to our code and see what's going on. So I've got this G-code interpreter. So that's going to initialize the motors. We're going to parse each line of that code that we've just looked at there. So we're going to say pass in one line. A line is going to be stripped of any white space before the code or the end of the code of the line. We're going to make it all upper. So in case it's got lowercase text in there, it's all going to be uppercase. And then if the line, if there's no text in the line, if it's just empty, which would be 2 speech marks, that'll mean that it's got nothing in it. Or if it doesn't start with G0 or G1, then return not supported. Just say ignore unsupported commands. Then we've got these parts. So we want to break up the different parts of the command. So if it's got G0, so like move, and then we want X, Y, and potentially the pen Z. So we will say parts equals split the line.split. That will split it into parts, will become a dictionary with potentially 3 different parts to it. So the command will be part 0 of our array, of our list. The target will be the self-position.copy. So it's going to make a copy of whatever is in self.position. Let's just walk through this a little bit further. So a copy is, in MicroPython, when you set a value to something, so say you say A equals 1, and then you say B equals 1, they're both actually pointing to the same thing, which is 1. If you then set C to be 1, all those 3 objects are pointing at the same value, but the value isn't really 1, it's kind of a container that contains 1, if that makes sense. If you then change what's in that container, it will update everything else that points to that. So we can have weird behaviors happen sometimes. So this copy command essentially makes another box to put those values in. So you get in a separate, unchangeable copy. So that's what that means there. So for part in parts 1, so this is the first of our, it might actually help if we put on some comments on here. So let's just do a little comment. So if our line is G0, X1, Y1, Z1, for example, let's just change them to 2 and 3 just to make it a bit easier to understand. So the command will be G1 in our case, G0, because it's going to take the 0th element of our array. So this array will look like this in theory, just so you can sort of visualize what's going on here. So parts will be the one element there, so that's going to be x. So part in part, so that's going to be from here. So that colon is interesting. So axis is part 0. So I think that colon there is saying take everything else to the end into part. So part is going to, let's just do another part equals, and then it's kind of that. It's like a little list. Axis will be part 0, so that's going to be x-axis, and if the axis is in x, y, or z, so x is in there, so that means it will accept that, and then the target axis is going to be, then this is interesting, we're going to convert whatever the value is to be an integer value, so it converts ints to steps. The part, we also want that to be a floating point number, so it might be the position that we get through. If you remember that G code that we had in here, these are floating point numbers, so we want to bring that in, and then part 1 will be, if we look at our part, that will be everything towards the end of that particular value. So if it's x1 not whatever, it'll take all the rest of that. That makes sense, because it might not just be x1, it might be x1.00, whatever numbers we had in there. So it'll take the rest of that value. So that's what will happen. We'll end up with axis, target, as you can see there, target x, target y, and target z. That's what will happen after this code is run through each of the x, y, z. If there's any issues, it just says continue, just ignore the issues and carry on. So d x, y, and z is like the sort of destination value that we want, and then the self dot position is going to be whatever it is minus that position. So whatever we currently have, take off that value from there. So it's going to move the motor when we actually send those values to our step motor, and then perform the movement itself. So if dx, if there's a value in there, then self motor move the absolute dx. The direction is 1. If the dx is greater than 0, otherwise move in the opposite direction. So that's the bit of code that actually moves the stepper motor. And the move command, if you remember when we looked at our stepper in there, we had a little function for move, and that will convert the steps to physical turnings of that motor. So that's where that happens in there. And then we're going to update the position based on all those target positions that we had in there. Once we've finished, we can change the direction or the position. We can pass in the x, y, or z, and then if the arguments are that are passed in there for axis in x, y, z, if axis is in the argument, so if x, y, z is in those arguments that pass through, then it will update the position.axis with whatever that value is. This k-args thing, that might look really, really unusual. What that means is if we passed in, for example, x equals 1, y equals 2, I'm putting equals. That's not how it would be like received by the function, but I'm just trying to sort of illustrate, what the value is and what the thing is that's coming in. These are arguments that are passed through, and it might be that there's a list of arguments, and what we want to do is break them out. So this star is a way of saying unpack whatever is in these arguments into their individual constituent things. So we've got x1, y2, z3. So that's what axis will become equal to that. And we can say for axis in those x, y, and z things, set the position to be x as it goes around the first time, and then y the second time, and then z the third time it goes around that little loop. So whatever the value is in there. Jog is going to move the motor without updating the position. So you can see there we pass in dx, y, and z, and we say if d is a value, then move the absolute position with the direction of equals 1. Otherwise, move it in the opposite direction. Direction is at 0. Yep, direction is -1. Sorry, and we do that for each of the 3 values that would pass through. That's all we have in our G-code interpreter. So it's pretty straightforward. Now we could see before when we were looking at this code that we have G003, so I'd actually have to look up what that does because we don't have that in our code currently. So G code, let us go to, let me load up a browser and we'll just have a quick look and see what G code 3 is. There's a really nice website that's got all the G codes on it there, so we can find out what that is. Let me just open up a browser and load it up. Just bear with me while I do that. So G code tutor, I think it is. And let's go over here. So I think on here there is a list of all the G codes that are available. Let's see. I had this before, so what I'm going to do, I'm just going to quickly find it. I'm just going to go to me for a second. I'm just going to search my history for that G code things. Bear with me. G code. G codes, there we go. Right. Okay. So G00 is rapid travel. G001 is linear travel, so it just moves at a set speed. There we go. G2 and G3 circular interpolation, so it'll figure out, rather than us having to sort of step through and figure out what a circle looks like and have each individual thing worked out there, we can just provide in like a radius value, and it will then figure out from that where to position that from. So you can see there, G3Y, radius of 10, and a feed rate of 100 in that particular example. So we don't currently have that in our code, we'll have to build that in, but we can add that to the list of things that we need to improve our code. Okay, let me just jump back to here. Okay, or maybe to over there. So that's our G-code interpreter. Right, so I've got a test USB piece of code. So this is kind of bringing together everything we've looked at already today. So we've got our stepper motors, we've got our G-code interpreters, and we're going to import system, OS, and select. So there's some interesting MicroPython stuff going on here. First thing we're going to do, we're going to connect our USB cable to our computer and to our Pico running MicroPython. Now normally when you do that, you get the, if I just run stop on here, I think I need to actually close that connection first on there. If I press stop, we get the REPL at the bottom down here. So let me just bring that up so you can see that when I click on stop. Just disconnect and connect it again, maybe that'll help. There we go. And I sometimes find that you just need to just go to Thonny and select either the RP20 or the Pico thing there. That sometimes seems to break it out of that main.py thing. Because I've got a file that's called main.py. If you've got that, when you provide power to your Pico, it'll immediately start running main.py. And main.py is just this test USB code that I've got currently open here, test USB. So what I'm saying is when we connect up a USB cable, we get the REPL. How do we run code so that we don't get the REPL, but we can output UART information, serial information? We can do that with this OS dupe term. So dupe term, we can either have that the console is enabled or not enabled, and the data is enabled or not enabled. There's like two different streams that we can send to the OS. So dupe term non-zero disables the REPL over the USB, and that means that we can then send text over USB as if it's just a UART connection. So we can receive that into other software. So that's the first interesting thing that we've not seen before. We're going to set up our motors like we've done before. We're going to set up a thing called G-code, which is using that G-code interpreter. We're going to pass in motors X, Y, and Z into that. And this steps per millimeter. So we now know that 1,000 steps equals 9 centimeters. So we probably need to change that value. That's probably why it's not moving currently. So let me just look out what that will be. So 1,000 divided by 9 centimeters is 101. So if I set that to be 111 steps per centimeter, is that right? So 1,000 steps is 9 centimeters. So that would be 900 millimeters. So it would be actually 1.1 step. 1 millimeter per step is probably about right. So it's about 1 millimeter per step. Let me know if that's right or wrong. Be interested to see if actually now that we've changed that, we could upload this code. I'm going to try that as an experiment. I'm going to say save a copy to the Pico as main.py, overwrite yes. I'm going to disconnect this, connect it back up, so it's going to run that main.py. I'm going to go over to, this is the CNC software. I'm going to connect up, click open. I'm going to load up that G code that we tried a second ago with the ABC. I'm going to try running it now. No, still doesn't move at all. I was wondering whether it would actually move or not. I wonder if it's to do with the speed. Nope. So that's interesting that didn't work. That's another little experiment that we've tried. So what else we've got on here? Right, so at the top of the file we need to define some descriptions. So when you use Gerbil, and again that's really for running on things like Arduinos and so on, it outputs statuses. So typically your G-code software such as this CNCJS, it's going to have a conversation, it's going to have a handshake with your Gerbil device. It's going to ask it what version of Gerbil are you running, what is the current status, what are your positions, and what state are you in? Are you in an alert state, are you in an idle state, and so on. So we need to be able to answer those and respond to those questions. If I come down here into this little CNCJS, this is what's connected to this USB modem 4. It's talking directly to my MicroPython code right now. So if I come in along here and I say $, it just responds back OK. We're not getting any interesting response. That OK text response back is some of my code running. If I do H, that should home the device. If I do I, that should tell me some information. Interestingly, it's not responding back with anything on there. And then what's the other one? Which is it? Just a single $. It's question mark. So interestingly, it's not responding back with anything on any of those, and that's not right. That means there's probably something wrong with our code on there. The fact it's responding back with OK means that it has understood that there is a command coming through, but because we're using the USB to talk directly to this streaming software, we can't actually have any error messages. That's one of the limitations of it. Right, so I'm just going to disconnect that. I'm going to go back to our code over here. So these Gerbil settings, these are kind of some made-up settings. They're not actually current or accurate at the moment. There's a whole bunch of them, and it's things like, how many millimeters per minute does your homing feed or your spindle, what's the maximum RPM, minimum RPM, and so on. Is the laser mode enabled? All these are different statuses that we need to be able to send to our Gerbil reader, which is that CNCJS. We've then got things like, these are some statuses that we need to keep track of when we're talking to this CNCJS. So the banner is when you very first boot up your Gerbil device, it needs to send a banner to say, I'm running Gerbil 1.1 and I'm ready to work. So there's a banner that it's expecting to receive. One of the other things that's tricky with MicroPython as it comes out of the box is you can't detect whether your USB connection has been made or not. So how do you know if a connection has been made? Now luckily these things like this CNCJS, they can actually detect, you can actually send commands multiple times. There we go. So I've just fired off 2 question marks. 2 question marks means is a way of a question mark is a way of asking, give me your status, give me, you know, what you're currently doing. And if it doesn't get a response back after firing one, it will fire another one to say, I'm going to retry. Here's another second question mark. My code can detect a second question mark, and it can go, right, I should probably send the banner. So I should send that Gerbil 1.1f $ for help. That's my MicroPython code running and giving a response back. It's then saying, if you do $H and $X, that will unlock the plotter. By default, they are locked. This is, if you've got like a laser, you don't want that to be like just start laser cutting without commands. So we have this lock and unlock kind of command. And then we've got all those 0, 1, 2, 3, 4 that we had in that little status thing before, which are all kind of fake commands, but they're there to respond. If we do multiple question marks in a row, we get that little banner being sent. So that's a way of detecting that we have got a USB connection. We'll typically get 2 question marks in a row from the software. So that's something that we can actually detect. So I've got this question counter for detecting that. The last question time is, well, what happens if we have a disconnection and we've already had 2 question marks? How do we know when to reset that question mark counter back to 0? And we can basically just have a timeout value. So this last question time is a way of having like a, when was the last time these question marks came through? When was the last time we sent a status? Ticks MS is how many microseconds have occurred since your MicroPython device has power. So that's like a value that's constantly ticking up. And then we've got some other things like the idle reset. So if we've not had any question marks for a long time, we can treat this as like a new session, because we've no other way of detecting whether it's been reconnected, disconnected, and so on. So the request interval in milliseconds, the gap between these question marks for that banner, and this is all to do with that kind of handshake between our software and this streamer. And we've got this status interval as well. So we want to be able to write and receive commands over the USB. So we need to use this standard out to write commands out, and we need to have standard in to receive commands in over USB. Normally you'd print out something to the console, but print has other stuff that you don't see. It has like carriage returns, it has new line, so there's all these extra characters that get sent. So R is like return character and N is new line. So return means, remember on typewriters, you get to the end of a line and you have to like press the thing and it makes the carriage go back. Computers emulate that in terminal software because they used to physically have like electronic typewriters to output stuff. New line will literally rotate the drum that the paper is on in a virtual typewriter. So we still have those commands for moving things around on screens. So when we're working with terminals, we still use R and N for that return and new line. So this poller thing is a way of having non-blocking input and output. Blocking output is if you're waiting for somebody to type something in, no other code can run while you're waiting for that. And that's going to mess up our code, because if we're waiting for something to happen, we still need to be updating, like, you know, the plotter doing stuff in the background. So this poller is a way of checking to see if there's any change, checking to see if somebody's typed something in from this CNCJS software. And we can register this this poller with the standard input, so we can select poll in, and that's just a way of kind of routing stuff internally in behind the scenes in MicroPython. So we've got this send status. This is going to send the current position, and we can output this with a sys.standardout.write. That's going to write to our USB UART device. We're going to output, and we've got there idle the position X, Y, and Z. Got the X position, the Y position, Z position. This kind of formatting thing is just a quirk of how that standard out works. So it looks very messy, but essentially it's swapping out position X with the first thing, position Y with the second thing, and position Z with the third thing in there. And this .3f is a formatting convention. We could probably look up what that means, but you could look at that too. Send banner is going to send the banner, so that Gerbil 1.1f, we've literally got 3 lines of text being sent out there, and for for each line in range 0 to 3, we're going to send the status. We're going to set our banner thing to true, and we're going to update. The last time we updated that banner to whatever the ticks ms is, and we can use this later on to detect have we already sent that banner in this session. We're going to then give our USB host a second to sleep. We're then going to have a while true loop, and this is going to go around infinitely while we've got power to our MicroPython device. We're basically going to update whatever the ticks ms is into our little now thing, and then we've got all this kind of state management that we need to do. So have we had any question marks for a while? Have we sent the banner? Do we need to resend that banner information? And this is just to do that handshaking information between our MicroPython device and whatever G-code streamer we're using. So that's what these banner sent things are all about. Check if there's any incoming data. So if not, poller.poll continue. So if there's no data, ignore it. If there is data, then we can read that data in using this line equals sys standard in read line. Strip it of any return a new line, so we just get the actual command that's come through. If there isn't anything in that line, then after we've done that, then we can just say carry on, go through the loop again. We can then handle these question mark probes. So if we get a question mark response from the G-code streamer that's asking for some information, we can then say if we've not had one of these for a while, is what this essentially says. If ticksdiff now, and the last time the question was asked, is less than the request interval time, then we can increment the question counter to 1. And if we have multiple questions, which we get in this line down here, so if the banner's not been sent and the question counter is greater than 2, so we've had 2 question marks come from our G-code streamer, we can send the banner and we can update that question counter back to 0, and then just go back around the loop. After we've sent that banner, we can then send the status, and they can say that the last status time is equal to whatever now is, which we updated before. Now we get into the next block of code, and this is about all the individual commands that come through from the G-code streamer. So if we get a soft reset, which is a control X, and that looks like /X18. So this is like a hexadecimal 18 ASCII character. Then we can say if the line is that, and the banner set the banner equal to false and set the question counter to 0. That's essentially us resetting our internal state. If the banner's not been sent and the line starts with $, we can send the banner. And then we've got these Gerbil style commands. So if the line is $I, we can output MicroPython Gerbil 1.1, and then we've got a bit of information about MicroPython USB 3-axis, and then we've got OK. We have to put that OK thing at the end of each of our lines. If we get the X, which is the unlocking thing, this will, if we have a laser or we've got a cutting tool that can actually activate that, we haven't got that in this case. We can just return OK and unlocked. If we get the $, that essentially says dump all the settings that we have, and that's why I had all those 0, 1, 2, 3, 4 with all the different settings that we've got. So that's a little loop to output all of those. If we get a G command, this is where we say output G91, G21, G94, and OK. We probably need to update that, because why are we outputting that command? What does that actually do? So what does this do? We need to understand that. We have the OK as well. If it starts with 92, we can again go back to that website that's got all those commands on there. So let's find that G92. I think we just went past it then, did we? G90, G92. G92. So let's see if there's a list on there what G92 is. Per minute feed, no, screw thread cutting cycle. So that's a lathe command. We don't need that. That's probably a bit of duff code that's there. So if it starts with that, I don't even know why we're responding to that, but there we go. If it starts with J, so that's the jog command. This is where we want to move the motors around, but without actually updating any position. So this is some code for doing that. Position. Otherwise, we just output the line. So all of the G-code motion stuff, we're just going to parse the line, output OK. If we get any exceptions, we just say that there's been an error. And that's all that we have in our USB test thing. So again, if I go back to our CNC.js, we can do, let's try one of those commands out. So it was it $I? There we go. $I. So we've got the banner being printed out. We've also got this MicroPython and then USB 3-axis bit and the OK messages. We had the home command and we had the X for unlocking. There you go. So X as unlocked. Caution, unlocked. OK. And this is the conversation that's happening between this G-code streaming software, which can send, in theory, an image that we've created. So there's a spiral one, for example. And in theory, if I press this play button on here, that is going to tell our... You can see the lights are flashing, but I think they're happening too fast for our plotter to be able to actually move and draw that picture. So that's one of the things I need to work on next. So this is why this is kind of a work in progress and why I'm in that messy middle part of the project where stuff isn't quite working. We've got to figure out why that is. And it might be to do with that short circuit that I had, or it might be something else entirely. Could be a bad stepper motor, but we've tested our stepper motors and we can see that they actually do work. So what I need to do now is just close that connection, and then I can go back to Thonny and I can click on stop, and I can then have a look at the code and run it manually. We can actually run this code without being connected to anything else. If I do that, the output is going to appear on here. So if I do question mark, it's now responding. We're getting through those positions. We could then do $G 0 x1 y1 z1. Okay, and I can see that it hasn't updated the positions, interestingly. We could do $, which outputs all of those statuses, and we can do $x, oops, I need to be down there, $x to unlock. You can see there we've got the unlock. And I think if you do it again it should actually lock it, but we don't have any code that actually interprets that properly. It just kind of fakes output. So there we go. That's the bits and pieces that we need to make our plotter actually work. There's still some work to be done there to actually get this working properly. So that's how we do it. We do little experiments. We ask a question, we figure out how we can answer that, and once we've got the answer we can then move on. It's just about breaking down your code into smaller sections. Cool, so if you want to follow me on Discord, we have a Discord community, not really follow, if you want to join our community, we've got this great Discord community. Jump over there. If you want to sign up, link, go to kevsrobots.com/discord and you'll get put your email address in, you'll get an email back within a couple of minutes from Discord themselves. And if you want to follow me on social media, I'm on all the social media platforms. So I'm on Threads at KevinMcAleer at threads.net. I'm on TikTok, KevinMcAleer6. I'm on Instagram at KevinMcAleer. I'm on X at KevsMac. I'm on Mastodon at kevsmac at mastodon.social. I'm also on Blue Sky at kevsmac.bsky.social. If you're on any of those, follow me and then just give me a hi. And if you've got any projects you're working on, you can also share some pictures of what you're working on too. I always like to see what people are working on. If you want to join me and get your name in the end credits, you can do that by going to kevsrobots.com/coffee. All the information is on there for you to be able to do that. So definitely welcome people to have a look at that and do that as well. And we have a number of people who have done exactly that. So let's give a shout out to all these people who've been very, very generous with both their time and their money. So Maria Louise Mayer bought me 3 coffees. Thank you so much for that, Maria. Really do appreciate it. And somebody that wanted to remain nameless also bought me a coffee. Thank you for that as well. You know who you are. Member-wise, we have an anonymous member. We've got Silicon Fiber, Marie TKD, we've got Jeff Johnson, DN Corty, Marlene, Brent, and Tom. That's on the Buy Me a Coffee side. And then on the YouTube side, I have to do this because I'm kind of reversed in which way I'm pointing. We've got Justice, we have PAs, we've got Orchstrad39, Bert, Marie, Michael, Steve, Ford, Bello, Johnny, Stephen, John Paul, Cassie, Tinkering Rocks, Johnny Bates, and of course we have Tom. Thank you all so much for supporting the channel. It means so much for me that you do this, and it means I can go out and buy a few more stepper motors to continue with my project builds. But this is one I'm going to be carrying on with. So thank you all for doing that. If I now go back to our slides, We get the little spinny logo. That tells me it's the time of the video where you should be recommending over here another video from the over 420-ish videos we've got on the channel so far. Handpick one just for you. Hopefully you'll like that one, and definitely binge watch as much as you can. That's all good for growth of the channel. So thank you so much for watching, and I shall see you next time. Bye for now.